All right, as we begin today, go ahead and open up your practice exercise booklet to practice exercise number 40. Practice exercise number 40, and let's see here. You may use a calculator. You may use a calculator for practice exercise number 40, and kind of all connected to each other in a way, similar theme at least, to the problems there. Go ahead and get started, pause the video while you work, and then when you're finished, resume the video, and we'll see how you did. All right, let's take a look at the answers to practice exercise number 40. The first problem says the driver of an empty bus picks up 7 passengers at the first stop, then drops off 3 at the second stop. So there's 4 passengers. Picks up 7 at the third stop, drops off 3 at the fourth stop. So in other words, every other stop, they're adding 4 more people, okay? If she continues, she refers to the bus driver apparently, in the same manner for 20 stops, how many passengers are on the bus after the 20th stop? And just to help you out, the answer is found quickly. If you notice, there are 4 additional passengers after every 2 stops, and you decide how many groups of 2 are in 20. Well, there's 10 groups of 2 in 20, 4 passengers every other stop, 40 passengers on the bus. So hopefully you got the first one correct, particularly with that help. All right, looking at the second problem. Driver of the bus filled the gas tank by putting in 21 gallons. The gas tank gauge was at 5/8 before she filled the tank. How many gallons does the tank hold? Well, here's the deal. If the gauge is at 5/8, how empty is it? It is 3/8 empty, right? It's at 5/8, so that means there's only 3/8 missing. But even though she's over half a tank, she's like, you know what, let me finish topping it off, make sure we're good. So she fills up the last 3/8 of the tank. And this 3/8 of the tank is 21 gallons, right? So since we don't know how full the tank is, we could say that 3/8 of or times x, because we don't know the fullness of the tank, is or equals 21 gallons. 3/8 times x equals 21. And to solve the equation, simply multiply by the reciprocal, cancel the 3 with the 21, get 1 and 7. 7 times 8 is 56. Okay, and so 56 gallons is the fullness of the entire tank of gas. A little bit of pre-algebra type stuff there. That's the kind of thing we did in pre-algebra, but we usually did it with percents, not fractions. All right, next one says, on Wednesday, the bus transported a total of 420 passengers. This number, 420, was 120% of the number of passengers who were transported on Tuesday. How many were transported on Tuesday? Same thing. The 420 passengers was 120% of the number transported on Tuesday, right? This number was 120% of number of passengers on Tuesday. Well, again, instead of was, we can put equals. That linking verb means equals, or a refresher from your algebra classes. 120%, of course, we don't want a percent. We're going to move the decimal twice and get 1.20 or 1.2. Once again, we see of, which means multiply. And since we don't know how many on Tuesday, that's what we're finding, we'll call it x. Well, just divide away. 1.2, and this is where it helps to have a calculator. 420 divided by 1.2 gives you a value of 350. So apparently, on Tuesday, there were 350 passengers transported. And the last thing, Mrs. Hare, the bus driver, received a pay rate of $8.70 per hour until she received a pay raise, which gave her $9.15 per hour. Find her percent of increase to the nearest whole percent. So again, a lot of pre-algebra here. This kind of stuff I do with my 8th graders a lot. She was at 870, but it went up to 915. When it says percent of increase, remember, percent of increase or decrease is found using the formula change over original. You find out how much did it change over how much was it originally. So we need to first of all figure out how much did her pay change. Well, from 870 to 915, what's that, 45 cents? And originally, I'm going to forget the dollar sign for now, originally she bet at 870. Now, since both numerator and denominator have 2 decimals, remember, knock it out. Right? Boink, boink, in the bottom, and therefore, what you do the bottom down to the top, boink, boink, and it's out. Or multiply top and bottom by 100. Okay, a couple ways to think mathematically of that. And again, I would use a calculator here, and I would say 45 divided by the 870. And since I am lazy, I'm going to go ahead and get out my calculator and do it that way. 45 divided by 870. And I get 0.05172, blah, 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 right? But it said what percent? So, 5.172, blah, 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 percent. Or if we round it off, it says to the nearest whole percent. Well, 0.1 is worthless, basically. So we'll just say 5%. And obviously, it was a 5% increase. But 5%, our answer there. So again, a good refresher from our pre-algebra days, our 8th grade year. And it's been a little while since we've done some of this. Also a refresher on some word problem type stuff we did in algebra as well, setting up equations. So good refresher. Again, that's why we do practice exercises, to refresh our memory on some of the things we learned in years past. All right, go ahead and set practice exercise 40 aside. And let's go ahead now and review over some things we talked about recently. We talked about a quadrilateral. We've talked a lot about quadrilaterals actually lately. And we've been talking about parallelograms, remember? Opposite sides parallel. But then we talked about a quadrilateral with only 2 sides parallel. The other 2 are not. One set of opposite sides parallel is how I worded it. What do we call that? Good, a trapezoid. Trapezoid. And we said that in a trapezoid, those 2 parallel sides are called the bases. Good. And the non-parallel sides are called the legs. Good. Assuming you're answering correctly, Victoria. Because of course I assume the best of you. You're related to me. How could you? Anyway. Anyway, I digress. We said that if we were to find the midpoints of the legs, those non-parallel sides, and join them, that line is called the median of the trapezoid. We mentioned a median in our last lesson of a triangle, which goes vertex to midpoint, whereas in the trapezoid, it's midpoint to midpoint of those legs. We also said that that median of the trapezoid is what to the bases? It's going to run parallel to the bases, parallel to the bases. Of course, it bisects the legs, but also any other line you draw from either of the diagonals, that you draw, it'll also bisect those as well. And we said that the length of the median is always equal to what? Half the sum of the bases. So several things to know about the trapezoid. For that matter, we said if you were to have equal legs to our trapezoid, we have something called an isosceles trapezoid, yes. And something special about the isosceles trapezoid. Not only are the legs equal, something else is equal in an isosceles trapezoid. No, not the bases. I'm kidding. Victoria didn't say the bases. She would not know. Bases couldn't. Well, did you tell me, could the bases ever possibly be equal? Because you have sides that are equal and parallel then. And if 2 sides are equal and parallel, you have a parallelogram, not a trapezoid. So no, bases are never equal. But what are equal? You said it, Victoria? Yeah, the angles at the bases. The base angles at the lower base are equal. The base angles at the upper base are equal. Also, good, diagonals are equal as well. So I have every confidence in you. All right, especially since I'm making the video specifically for you. We also talked about location theorems. Remember, if a line, or if a point, lies in the bisector of an angle, it is equidistant from the sides of the angle. What if a point's equidistant from the sides of an angle? Yeah, it's in the angle bisector. What if a point is equidistant from the ends of a line? Yeah, it's in the perpendicular bisector of the line. What if a point is in the perpendicular bisector of a line? Equidistant from the ends of the line. Yes, okay. We talked about lines, 3 or more lines that all meet in the same point. The concurrent lines. There's 4 sets of these concurrent lines we need to know. If we were to draw the angle bisectors of the sides of the angle bisectors in a triangle, the bisectors of the 3 angles of a triangle, those angle bisectors will meet at the in-center. You did a better job with your answer than I did with my delivery on the question. Good. In-center. What if we were to draw the 3 medians of a triangle? Where would they intersect? Because that's what we talked about yesterday, the centroid. By the way, I failed to mention yesterday, the centroid is actually the true center of the triangle, the center of mass, if you will. So for instance, if you were to cut out a triangle out of cardboard or something, and you wanted to balance it on your finger so it would stay perfectly level, you'd have to balance it at the centroid. Okay? Anywhere else it wouldn't balance. What if we were to draw the perpendicular bisectors of the sides of the triangle? Those would meet at the, careful, circumcenter. And what about the three altitudes? Those meet at the orthocenter. If you didn't know those, make sure you work on those. We also talked yesterday about different ways to approach proofs. We're going to spend some time working on proofs a lot. And said that one approach to proof is to look at the given and say, well, this is true, so this must be true. And if that's true, then this must be true. Well, if that's true, then this must be true. And lo and behold, look, I just discovered what it said to prove. If you just make known statements starting with the given until you arrive at your conclusion, it doesn't usually work. Sometimes it does, but usually not. But what is that approach called, or that method of proof called? The synthetic approach. The synthetic approach. Now, another way to look at a proof is to say, all right, what am I trying to prove? Well, I know I could prove this true if this were also true. And this would be true if this were true, and this would be true if this were true, and this would be true if this were true. Hey, look at that, that's in the given. I'm done. Okay? Kind of working backward, where you begin by focusing on what is to be proven and determine what statements are needed to make that conclusion. That method of proof is called the analytic method. That's that analysis step, if you will. And I said, really the best approach is which one, synthetic or analytic? Trick question. I can't tell if I got you or not. Neither, right? The best approach is both. Start synthetic, though. Start with, what do I know? What's Clang? Get everything you can. Then, once you run out of Clang, what am I trying to prove? Okay? How do I get that? If I get this, how do I get that? If I get this, how do I get that? If I got this, but that's already up there. That was from my Clang. And it meets in the middle. So start synthetic, work your way down until you get to a stopping point. Get to what you're trying to prove, and you don't have to write it down, but at least mentally think, this is what I need to prove. I need to know this. I need to know this. I need to know, oh, that's already there. And work your way backwards to meet in the middle, if you will. Kind of like if you were taking a trip. And maybe you were using a map instead of your GPS. It's like old school Victoria, like really old school. I don't know if you've ever done this before. I have. Maybe your dad has. But take a trip using a map. And you say, well, I know how to get out of my neighborhood, right? I know how to get, for instance, to the interstate. So that's like your Clang. Okay, I know how to get to the interstate. All right? And I know the interstate is what kind of connects us. Let me now look at the location I'm going to. All right? Well, this location, I want to get to this main road. And from this main road, it connects to this road, which connects to this road, which connects to, oh, the interstate. And it meets in the middle. That's kind of the idea here of how to put together our proofs. And page 119, number 5, your homework for last night, maybe used some of these techniques. So let's see how we did on our proof from last night. Given a rather unusual shape, it was a slightly obtuse triangle, triangle A, B, C, and you were given a median CD. Now remember, again, median, vertex to midpoint, so there's a Clang right there. So there we go. And but this median then extends out, kind of like our last homework proof, and there's a line from A that goes perpendicular. Of course, we know that there's only one line from a point that can be drawn perpendicular to a given line. So as I extend the line indefinitely, only one perpendicular can be drawn. That's this line here, AF. It says is perpendicular to the extension of CD. But we also have a perpendicular from B we can draw, and we draw the one and only perpendicular from B. And we want to prove that the perpendiculars are equal to each other. So let me just come over here and we'll get started on our proof, because I'll get the given down here. I'm lazy, don't want to write it more than once if I can help it. All right, so our given, we were given a triangle ABC with median CD. We were given that AF and BE. or each perpendicular to CD, or we might say CDF, for instance. And of course, that is all given. Hopefully, you started synthetic. Like, I don't even have to think about what I'm proving yet, though I have mentioned it. I got Klein median. Hopefully, you learned from the previous night's homework, right? And you said, well, that means that D is the midpoint of AB, based on the definition of a median of a triangle. If you forgot that step, if you just went straight to AD equals BD, why are AD and BD equal? Because you have a midpoint, but you have to state that you have a midpoint. So this is an easy statement to forget. It's easy to jump straight to AD equals BD, but not definition of median, definition of midpoint. The definition of a median does not say a line that divides another line into two equal segments. That's a midpoint is a point that divides a line into two equal segments. A median is a line that goes to a midpoint. So make sure we get both of those on there. I got perpendicular, right? Clang. Yeah, right angles. I've got a right angle at F. This point was called E, correct? Yeah. So I've got a right angle right here. And we can say number 4 that angle F and... well, I can't say angle E because there's 2 of them. Now, technically, they both are right angles. Tell you what, I'm going to number this angle 1. I'm going to number this angle 2. And we'll just do that. Instead of angle F and angle BED, because I don't want to give anyone thoughts of going to bed right now. Angle, no, I know it wasn't a good joke, sorry. Angle 1 and angle 2 are right angles. And how do we know they're right angles? Yeah, definition of perpendicular lines. Now, I actually started to write this by accident. I started saying angle 1 and angle 2 are equal. Careful. I don't want to say 1 and 2 are equal yet. I need to say they're right angles. And because they are right angles, we know they are equal because yeah, all right angles are equal. So they're equal to each other. I think that's about all the clang I've got, right? I have a median, which gives me a midpoint, which gives me equal segments. I've got perpendiculars, which give me right angles, which give me equal angles. Now let's think about what I'm trying to prove. I want to prove the perpendiculars are equal. AF is equal to BE. Well, if these two lines were in the same triangle, I would say, well, let's get them across from equal angles. Equal angles, equal sides. That's an A triangle. I have 2 different triangles. Oh, so if you want equal line segments in 2 different triangles, let's try to get the triangles congruent and use CPCTE, right. So I can, if I want to, come down here to the bottom of my proof and say, I know that I'm going to be able to get AF equal to BE. Okay, I have confidence in my abilities in that regard. And I know I'm going to get them equal, because they're in 2 different right triangles. I'm going to get them equal by CPCTE, because I'm going to get triangle ADF congruent to triangle. Now I want A and B to line up. So B, and I want E and F to line up. So I should say BDE. I want ADF and BDE to be congruent. Now I don't know how I'm going to get them congruent yet, but I know I'm going to get them congruent. And I've already got 2 sides equal here, and I know I've got 2 angles equal here. I just need another set of sides or another set of angles. Thoughts? Yeah, hopefully you were thinking of the vertical angles, right? We'll call them 3 and 4, but if I just get angle 3 equal to angle 4 because, yeah, vertical angles are equal, there's my other set of angles, and here I've got side, angle, angle. Number 7, the triangles are congruent, and therefore number 8, AF and BE are equal by CPCTE. Most of the proof was synthetic, but I wouldn't have arrived necessarily here without the analysis. Now maybe you're just like, anytime I see vertical angles, I'm going to say they're equal. Okay, that's fine too. But here we use the synthetic to start, switch to analytic, and we found the missing link, if you will. Missing links only happen in geometry proofs, never in the geologic column. Anyway, questions? on this, make sure you reach out to me via email and we can go over it more in depth, or rewatch the video if you think that would help you. Flip back or look back across the page. We're going to do just a couple more proofs together here. Number 1 on page 118. Number 1 on page 118. Go and copy down that picture. And there's a couple things we're going to try to prove here. A couple things that we want to prove in number 1. Of course, anytime there's multiple things to prove, we want to make sure we prove them in the order that they're asked of us. And that's going to be beneficial too. You don't try to overthink things. The book and test writer are kind to you in that regard, giving you the desired order of things. So we've got this big isosceles triangle ABC. I say big, it's wide, wide and flat. And from here, from C, we draw a line, just any old line down here, call this point D. But however big this piece is, we're in a sense going to measure off that same length and draw a line down here so that AD and BE are equal to each other. And of course we know it's isosceles, we've got these equal sides AC and BC. So there's our given. Again, where it says if this is true, given that this is true. If AC equals BC, and if that AD equals BE. Two things we want to prove. First of all, let's prove that triangle ADC is congruent to triangle BEC, and then also prove that triangle AEC is congruent to triangle BDC. All right, let's get this down. 2 columns, statements, reasons. Get down your first statement and your first reason. I want you to take a few moments. I want you to see if you can think through how you should start on this proof. So go ahead and start it out on your own. Take just a few minutes, maybe pause the video. And then once you think you've got it, or you're completely stuck, or maybe you work through a little ways and you think you're on the right track, and then, but I can't figure out how to finish, at some point go ahead and resume the video. But for now, pause it and work. If you're in a class setting, maybe pause it for about 3 minutes to give students time. All right, let's see how we did here. First of all, we should have noticed that ADC and BEC are referring to as little slivery triangles, right? And with the little slivery triangles, I have a side equal to a side. I have another side equal to another side. So right here, I'm either going to use side, 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 or side, angle, side, right? The two methods that involve two sets of sides. I either need to get these two sides equal to get side, 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 right? Or I need to get a pair of angles equal, but it's not any pairs of angles. For it to be side, angle, side, it would have to be side, angle, side. This angle at A would have to be equal to this angle at B. And hopefully that's what you locked in on. That since this is a great big triangle, yes, I know it's been broken into 3 little pieces, but it's still one big triangle. And if I've got 2 equal sides, I've got 2 equal opposite angles. And hopefully, number 2, you said that angle A was equal to angle B because angles, opposite equal sides in a triangle are equal. And if you did, there's your side, angle, side. And we've got number 3, the first thing we want to prove. Triangle ADC congruent to triangle BEC by side, angle, side. I am hopeful, okay, we should have gotten this far. At this point, we should have made it this far. Let's see about the next part. Now we want to prove that triangle AEC. Okay, now that's this whole thing here is congruent to triangle BDC which is that thing there. Remember my suggestion to you long ago, if you have overlapping triangles, try to unoverlap them. So maybe off to the side, A, E, C, oh yeah, D is somewhere along here. And we've got the other triangle over here, B, C, D. And this is poorly drawn because it actually, trying to draw it more to scale, actually looks more like this, doesn't it? All right, so I knew that AC and BC were equal. That was given. I was given that this little piece and this little piece are equal. I have since discovered, or proven, that these two angles are equal. You say, well, is it that side angle side? No. I don't know that this whole side and this whole side are equal to each other yet. Oh, yeah. I only know that this part of a side is equal to this part of the other side. Oh, sounded a lot like the homework proof we did a couple nights ago. If you think you're onto it, pause the video. Now, if you're in a class setting, you can't do that. But, yeah, hopefully we thought, well, I know that the whole thing AE is equal to the sum of its parts, AD and DE. And I know that this whole thing, BD, is equal to the sum of its parts, BE and DE, because the whole equals the sum of all of its parts. All right? And furthermore, I know that AD and BE are given as equal. And DE must be equal to itself by identity. And therefore, if I took equal quantities like DE and DE, and to these equal quantities, I added other equal quantities, like, say, AD and BE. Well, they have to be equal because of the addition axiom. And since AD and DE together make AE, then in place of this, I can substitute AE. And since B and D together make BD, I can substitute BD. And therefore, those are equal by substitution. And therefore, I do know that this whole side and this whole side are equal to each other. So I do have sides, angles, sides. So, sure enough, number 8, we know that triangle AEC and triangle BDC are congruent by a different side, angle, side. And that's page 118, number 1. If you got it, if you nailed it, let me know. Okay, if you missed a little something, okay, that's fine. Hopefully you figured it out now. If you were way off or somehow I lost you, make sure you let me know that. Let me help you. Let's do one more proof, and then we'll be done for this lesson. Page 119, top of the page, the very first proof on the page, page 119, number 3. Page 119, number 3. I want you to read it out loud to yourself 3 times while I erase the board. If you're proctoring the video, and if this is a class setting, please pick 3 different students to each read it 1 time. I had you read it 3 times because no picture's provided. When you have to provide your own picture, you want to read the statement very carefully, the problem very carefully a few times. Make sure you understand what it's saying. The bisectors, so I'm going to bisect some things, of the base angles of an isosceles triangle are equal. That's what I'm trying to prove. Well, what do I need to draw? Bisectors, but you have nothing to bisect. Base angles, but you have nothing to put them on, of an isosceles triangle. That's where we're going to draw first. So on your paper, draw an isosceles triangle. Now, I drew it tall and skinny. You could draw it short and flat like our last one. That's fine, however you choose to do it. And now let's call the triangle, oh, I don't know, ABC. Let's be boring. All right, triangle ABC. I was going to use you, Victoria, but I can't remember your middle initial. I'm sorry. Sounds like VW. Like car. Anyway, Volkswagen. Or maybe it's like the buddies. Anyway, anyway, forgive me. I'm a horrible uncle. Anyway, so we got our triangle ABC. And we want to bisect the base angles. So the way we've got it drawn, A and B are the base angles. We're going to bisect, to the best of our ability, angle A. We're going to bisect, to the best of our ability, angle B. And at some point, these bisectors have to meet. Let's call this point, here we go, V for Victoria. All right, and so we've got our bisectors. So we're given an isosceles triangle, ABC, with, we should specify the equal sides, AC equal to BC. And isosceles means two equal sides. We need to specify which ones. By the way, that makes A and B the base angles. We're also given that AV and BV bisect angle A and angle B respectively. And let me slide this out of the way just a little bit, make sure it's not in the way here. We want to prove that these two bisectors, AV and BV, are equal to each other. I want to prove that the bisectors themselves are equal to each other. Now there is a strategy tip here, something that will make our life a little bit easier. Maybe think about it as you're writing down your statements, reasons, getting down that first statement and first reason. So we're given isosceles triangle ABC with AC equal to BC. We're also told that AV and BV bisect angle A and angle B respectively. And of course, that's given to us. So let's think for just a minute. What strategy tip might we employ here to make our life a little bit easier? Yes, Victoria. Ah, great suggestion. We've got several angles here, so let's number them 1, 2, 3, and 5. And that's I think, going to help us out here. We don't really need to number the angle at V or the angle at C, right? They're standalone angles. Let's get started. In fact, I'll let you get started for just a few moments. So once again, pause the video for just a few minutes and then resume. All right, let's see how we did. There's a lot of clang in here. The first clang I see is equal sides in the same triangle. Clang! Equal angles. So hopefully you said that angle B and angle A are equal to each other because angles opposite equal sides in a triangle are equal. And then hopefully you saw this word bisect and like, well, clang, that means I've got some equal angles as well. That means 1 and 2 are equal to each other. And it means that angle 3 and angle 5 are equal to each other, or however you numbered your angles. The reason, definition of angle bisector. And that's about it for the clang, right? I got equal angles here, and then I got bisected equal pairs of angles. And I'm trying to prove that these segments are equal to each other. Well, these two lines, are they in the same triangle or are they in different triangles? Yeah, they're in the same triangle. Now, if they were in different triangles, I'd try to get congruent triangles, use CP, CTE, but they're in the same triangle. So I don't want that. I want to say, if these are in the same triangle, to get two lines equal in the same triangle, show that the opposite angles are equal. I want to say 2 and 3 are equal. But I don't know that 2 and 3 are equal. I know that 2 and 1 are equal. And I know that 3 and 5 are equal. Because after all, that's what a bisector does. It divides into 2 equal angles, right? Or we might say it divides into 2 equal halves. And And remember my suggestion. If you've got one thing bisected, don't say, then it's fine to say these two things are equal. But if you've got two things bisected, especially things that are equal being bisected, don't say angle 1 equals angle 2. Don't say angle 3 equals angle 5. Say that angle 1 and angle 2 are equal halves of angle A. Similarly, angle 3 and angle 5 are equal halves of angle B, because now angle 2 and angle 3 are equal halves of angles that are equal. And so we can say, number 4, that angle 2 equals angle 3 if I'll say equal halves instead of just equal angles. Reason here, of course, would be halves of equals are equal. We've seen this a few times now this year. Okay, so hopefully we're starting to see when to use that equal halves thing. But yeah, 2 and 3 are both halves of equals. Halves of equals are equal. And therefore, if I have two equal angles in the same triangle, ABV, then the angles are equal to, then the sides are equal. So number 5, we can say that AV and BV are equal to each other, because now the converse of what we said for our reason number 2, sides opposite equal angles in a triangle are equal. And there we go. 5 steps, and we've got it. How'd you do? If you nailed it, let me know. If you were, whatever, you got it now, then that's fine. If you struggled, though, let me know as well. Homework for this evening, page 119, number 8. Page 119, number 8. You've got your picture provided there, you're given, and we're looking to prove something there. All right. See you tomorrow. Have a wonderful rest of your day. And I just lost something here.